Yeah, welcome to the class. So we will continue our topic, which we started last week, excavator. So we covered up to, let me go, drag lines. We have already covered clamshells. And then we were talking something like about trenchless technologies. Okay, so we are going to start from the cranes. Okay. So for the cranes, as you can see that these are one of the very prominent machineries which we see on a construction project. Okay, so cranes are primarily used for lifting, lowering, and transporting loads. So these are their basic functions. They move loads horizontally by swinging or traveling. So both types of motions, swinging and traveling, take place. Most mobile cranes consist of a carrier and a superstructure equipped with a boom and hook as illustrated in figure 322. So in this case, there is this carrier, there is this superstructure, there is this boom. So, and a number of cables are here with which the crane is consisting of. The current trend towards the use of hydraulically operated equipment includes hydraulically powered telescoping booms. The mobile telescoping boom cranes shown in figure 323 is capable of lifting loads to the top of a 24-story building. That means if this type of boom may be used, so this is a telescoping boom. So in this case, the loading arm of the boom can be extended in the, with the help of the telescoping action, and then they can provide the loading up to a lot of for a lot of stories, such as is mentioned over here, up to 24-story high they can reach. The major factor controlling the load that may be safely lifted by a crane is operating radius. So when using the crane, it is a very important characteristic that the load to be lifted should be estimated well. So the load to be lifted by the crane depends on the operating radius of the crane. If the operating radius of the crane will be more, there will be more overturning moment on the crane. So if there will be more overturning moment on the crane, that means the load carried by the crane should be less. So the proper control of the weight which the crane is carrying is important for the operational safety in the crane. So this is a function of boom length and the boom angle above the horizontal. So operating radius means the horizontal distance from the center of the rotation to the hook. So this is a function of boom length and boom angle above the horizontal. Some of the other factors influencing a crane's safe lifting capacity include the position of the boom in relation to the carrier, whether or not outriggers, that is beams that widen the effective base of a crane are used, the amount of counterweight, and the condition of the supporting surface. So the sometimes the beams are used, so which effectively widen the base of the crane. So that means we want to provide more support to the beam, so that to the crane, so that it can carry more loads. The counterweight at the base can also be increased to improve the capacity of the crane, and also the load carrying capacity about the condition of the surface on which the crane is placed also depends. So the cranes consist of the, for example, if you just take like a crawler mounting crane, it will start from the crawler mounting crane. Then there will be a revolving deck where normally for this type of plane, for this type of crane, the operator will sit. And then there will be the boom, which will help to carry the load. There will be the hoist cable, the boom tip jib, and the hook will be also there. And this was the, as we have seen before, this is the large mobile hydraulic crane with the telescoping boom. Telescoping boom. Then there is this large crawler mounted lattice boom crane. So this is a crane which is a lattice boom. So there are three types of cranes. So this type of crane is a crane with the ring attachment. So it carries the load on the both sides of these booms. So this is a double boom crane. Okay. So another family of the cranes are the tower cranes. Okay. So the tower cranes are those cranes which rest on the top of the building. So another special type of crane is the tower crane, so which is illustrated in figure 3-28. So earlier, these cranes which we seen over here, they are called as the mobile cranes. So because they move from one location to the other locations, whereas the tower cranes remain on the top of the building. And then from there, these cranes control the operations. So another special type of crane is the tower crane, which is illustrated in figure 328. So as you can see that this is a tower crane. So this crane is fixed at one location. And then from that location, it control in the area within the reach of the crane. So depending on the size of the construction site, we may need one or more tower cranes on the construction site, so which can cover the site area according to the needs. So climbing cranes. So the tower crane is widely used on building construction projects because of its wide operating radius and almost unlimited height capability. Because these type of cranes can be moved upwards when the building is constructed. So with the progressive construction of the buildings, these cranes can be moved upward, and then they can provide almost unlimited height capability. So major types of tower cranes include horizontal jib cranes or They are also called as the saddle jib cranes. Luffing boom cranes and the articulated jib cranes as illustrated in figure 320. So what are these three different types of cranes? So this is the horizontal jib crane. As you can see that the jib of the crane is horizontal. This boom of the crane is horizontal. And the luffing boom crane, in this case, the boom is in the inclined position, which is supported by a cable over here. And then there is another one, which is the articulated crane. So articulated jib crane. So in this case, there are two booms, and then both booms are supported by those cables. So one of these three types of tower cranes are common. So the majority of tower cranes are the horizontal jib type cranes, so which is shown in figure 328. However, the luffing boom crane, that is with the inclined boom, models have the ability to operate in areas of restricted horizontal clearance. So in the horizontally, if the area is not too much, so then luffing boom cranes can be used, which are flexible in decreasing the horizontal reach of the building, horizontal reach of the crane. Operate in areas, these cranes, luffing boom cranes, operate in areas of restricted horizontal clearance, not suitable for horizontal jib cranes with their fixed jibs and counterweights. In the horizontal jib type of cranes, if the crane size is too big for the construction site, it is not possible to remove that horizontal jig to decrease the horizontal jib. So in those cases, luffing boom cranes is used. Also, the articulated jib cranes are able to reposition their hinged jibs to convert excess hook reach into added hook weight, into the added hook height. So thus such cranes can be operated in either the horizontal or luffed positions. So articulated jib cranes can work for both types of cranes. I mean, they can also work in the horizontal or in the luffed boom crane position as well. So types of tower cranes by the method of mounting include static, that is the fixed mount tower cranes, rail mounted tower cranes, or mobile tower cranes, and climbing cranes. So one of these four types of tower cranes can be used. That is the static, which remain fixed, rail mounted tower cranes. So some kind of railing is applied on which the tower crane is based. So within the reach of that railing, the tower crane may be moved. Mobile tower cranes are also available, and the climbing cranes are also available. So which climb up the building as the building progresses from one story to another, to the third story, to the fourth story, etc. The climbing cranes are supported by completed building floors and are capable of raising themselves from floor to floor as the building is erected. Okay, so this is how the climbing cranes work. And then for most of the high-rise buildings, then these climbing cranes are then very useful. So most tower cranes incorporate self-raising masts. That is, they raise themselves section by section until the mast or tower crane reaches the desired height. The tower crane capacity depends on the operating radius, amount of counterweight, and the mounting used. So the lifting capacity of a representative horizontal jib tower crane is shown in table 310. So Some types of tables can be used to determine the lifting capacity of the tower cranes. Well, this figure shows the different parts of the tower crane, and uh, and the length, the height of the tower crane can also be changed when the floors are being constructed. So generally, a crane will come with such kind of table. So this is just as an example. So from this table, we can see that if the lifting radius is 33.5 meter, and the boom length is in terms of feet and meter is about 79.2 meter, then this machine can lift a load of 9,781 kilogram. So this is for a relatively smaller radius and smaller boom crane. If the boom length is more, that is the boom length is over here. If the boom length is more, that is the maximum hook radius, then the load lifted can be 10,708 kilometers. So there is a lift radius, and then there is this boom length as well. Okay, so the weight of the hook block has been incorporated into table 310. However, the weight of all other load handling devices must be included in the calculated weight of the load. So it is also important that what type of, when we are saying that this much is the capacity of the train, of the tower crane, then we should be very clear that what type of loads are included into the capacity. So as an example, in table 3-10, the weight of the hook, which is being with which the loads are attached, are included into the are incorporated into the values which are provided by this table. However, the other weights, handling devices, they must be included in the calculated weight of the load. So they are, they must, so for example, if the load is, say, 2000 kilogram, and other additional loads for that will be like 100 kilogram. So that for the lifting purpose, that 100 kilogram load must be subtracted to see that, must be added into that 2000 kilogram. So then it will be like 2100 kilogram load that that will be carried by the crane. So the actual load which is being lifted, and then all the other supporting loads, handling loads, must be also included in the lifting operations. So we have this. So in this case, we have this different terminologies which can be used in the cranes. So this is the terminology of a horizontal jib tower crane. So this is the horizontal jib, and then this is the counterweight. Okay, counterweight over here. So as you can see that the lift, there is this boom length, that is the maximum hook radius, and then this is the lift radius. So both we need, both types of radii will be needed to find the capacity of the crane. Okay, so a crane can be used with the certain attachments. So a number of attachments besides the basic hook are available to assist the crane in performing the construction tasks. So crane can be used for mainly for lifting and lowering and transporting the loads from one location to another location. However, there are some other purposes with which the crane can also be used. So these different purposes can come because of the different crane attachments. So these are the different crane attachments. So as we have said that sometimes the clamshells can be also used. And in the show, so that is the digging tools can be also attached to the cranes. Different types of hooks can be attached to the cranes. Different types of grabs can be attached to the cranes, and some bulk material tools can be also attached with the crane. So for example, this is the concrete bucket. So cranes can be also used for carrying the concrete and then placing it into the areas where the concrete is required. Skips, bottom dump platforms, load platforms, pile drivers, skull crackers. So that means for breaking the hard materials, the skull crackers can be used. And these types of grabs help to hold the materials. So for different types of materials, there will be different requirements for holding the materials. So sometimes grabs can be used, sometimes hooks can be used, sometimes the loading platforms can be used. On the other hand, the digging tools may be used, such as the attachments for the clamshell buckets and the orange peel buckets. So these attachments have different types. Among these attachments, we have the concrete buckets, slings, special hooks, and load dropping tools. Weights are almost often used in the construction application. The skull cracker or the wrecking ball is a heavy weight that is hoisted by the crane and then swung or allowed to drop free to perform like a huge sledgehammer. So it is used to break up pavement and for demolition work. The simplest form of pile driver, a drop hammer, uses a similar action to drive the piles as well. So the hammer is hoisted and then dropped onto the pile cap to hammer the pile into the soil. So various types of heavy weight operations can be used with the help of those crane attachments. Okay, so with this, this topic is completed. So in this topic, we have covered various types of excavating and excavating and lifting equipments. So our next topic will be, which we are going to start now, will be for which will be topic number 8, which will be for loading and hauling equipment. Okay, so we can start this topic now. So do you have any questions? No questions. Yeah, okay, now I've started now. And so topic number 8, loading and hauling. Okay. So in the loading and hauling equipment, the purpose is to carry the load from one location to another location. So these locations are at a relatively greater distances. For example, these are not like on a very small site. If it is on very small site, then maybe cranes can be used to move the loads from one location to another location inside of the site. But if the distances are greater, then we need some special types of equipment. These are called as the loading and hauling equipment. So in those equipment, we need to estimate the equipment travel time. So that's why we are starting from the determination of the equipment travel time. So in calculating the time required for a haul unit. So haul is a term which is used for carrying the materials from one location to another location. Okay, so for a haul unit to make one complete cycle, it is customary to break the cycle down into fixed and variable components. So the cycle time for the hauling operation will consist of some fixed time. That means every time um, this much of time will be consumed. And then there will be a variable time, so which will depend on some factors such as the distances, speed, etc., on which the time will change. So we need to determine the fixed time, and then we need to determine the variable time. So fixed time represents those components of cycle time other than travel time. For example, spot time, that is moving the unit into position to begin loading, load time, maneuver time, and dump time. So maneuver time means just certain adjustments into the machine are being made to bring the machine into the proper position to work. The variable time represents the travel time required for a unit to haul the material to the unloading site. So loading and then unloading, okay? So this is the variable time, so which is the travel time basically. So when talking about such times, then the machines or the trucks or other equipment which is used for transportation, they move on the surface of the earth. So when these machines move on the ground, so there will be a resistance from the ground for the movement. So that resistance is called the rolling resistance. So determine the maximum speed of a vehicle in a specific situation. It is necessary to determine the total resistance to movement of the vehicle. Because normally these transports will not take place in very good quality paved highways, because the construction operations are normally taking place in remote areas. So a rolling resistance, that is the resistance provided by the ground in against the traveling motion, may be very important in those situations. So the resistance that a vehicle encounters in traveling over a surface is made up of two components: rolling resistance and grade resistance. So rolling resistance depends on the type of surface. Okay, for example, sandy soil, a clay soil, rock, etc. So this is the resistance provided by the type of this. And the grade resistance. Grade resistance depends on the slope of the surface, sloping up, sloping down. Okay, so the total resistance is then the grade resistance plus the rolling resistance. Okay. For typical values of the rolling resistance can be determined by this table. So for example, if it is a concrete or asphalt surface, that is the pavement on which the trucks are moving, are made of concrete or asphalt, then the rolling resistance will be about in terms of the kilogram per ton, it will be about 20 kilogram per ton. Okay, 20 kilogram per ton. And there are some values in the parentheses as well. In those situations, some other types of tires are used. On the other hand, for some other for some other type of surfaces, for example, if it is a loose sand or gravel, in those loose sand or gravel, the rolling resistance will be much higher, will be 100 kilogram per ton of the weight. Per ton means 1000 kilogram. And then there is this PO and the other type of ton, which is in the US customary units. It is about 2000 pound. So ton and ton are different over here. So normally we are preferring the SI system of units. So if it is soft, muddy, and deeply rutted surface, so the rolling resistance will be even greater. There is another equation which is called as the rolling resistance factor, which is 20 plus 6 times the centimeters in the penetration. So this rolling resistance factor. So typical values of the rolling resistance factor are given by this. So in addition, some adjustment is also made to determine the formulas. Okay, so this is just as an example. It is shown over here. So let's see one example later on. On the other hand, as we have said that the total resistance is the grade resistance plus the rolling resistance. We will be using these formulas in the calculations. So let's see the grade resistance. So the grade resistance is grade resistance represents that component of the vehicle weight which acts parallel to an inclined surface. So if, for example, if the vehicle is moving on a grade, if the vehicle is moving on a grade, so this is the horizontal surface, and this is the inclined surface. Okay, so a certain component of the weight of the vehicle, so for example, this is the weight. So for example, this is the weight. So one component of the weight will be perpendicular to the surface. The other component of the weight will be in the parallel to the surface. So this component of the weight will be because of this slope. Okay, this angle alpha or beta, whatever will be the angle. So the component of the weight which will be parallel to the inclined surface, that will provide the grade resistance. So when the vehicle is traveling up a grade, okay, when the vehicle is traveling up a grade resistance is positive. And when the traveling downhill the grade, then the grade resistance is negative. So which is obvious that if moving down the grade, then less resistance will be there from the grade resistance, so that will be a negative grade resistance. On the other hand, it will be a positive grade resistance. Okay, so the grade resistance factor in those situations will be given by if the weight is will be given by 10 times the grade percentage of the grade. And grade resistance may be calculated using equations 4.5 or 4.6. So that is the grade resistance in terms of the kilogram is equal to weight of the vehicle multiplied by the grade resistance factor, grade resistance factor. So which will be 10 times the grade in the percentage. And the grade resistance in the kilogram will be equal to the vehicle weight multiplied by the grade as well. So one of these formulas may be used in the calculations purposes. Okay, so these are the grade resistance formulas. Okay, and after that there will be example 4-1. When we will do the example, then these calculations and the use of these equations will be relatively clear. Okay, then there is a concept of the effective grade. So effective grade is the total resistance to movement of a vehicle. The sum of its rolling resistance and grade resistance may be expressed in pounds or kilograms. However, a somewhat simpler method for expressing total resistance is to state it as a grade percentage, which would have a grade resistance equivalent to the total resistance actually encountered. So to make things simpler, instead of representing the grade resistance in terms of the kilogram or pounds, those resistance values may be converted into an equivalent percentage of grade. So that is called, that will be called as the effective grade. So this method of expressing the total resistance is referred to as the effective grade, equivalent grade or percent total resistance, and is often used in manufacturers' performance charts. So the effective grade is equal to the grade percent plus the rolling resistance factor divided by 10, okay, in terms of the kilogram per ton. Okay, so let's see the example. A wheel tractor scraper weighing 100 tons or 91 tons, that is 100, these TONs tons means 100 times 2000 pound, okay, but in kilogram terms it will be 91,000 kilogram, okay, 91,000 kilogram. So it will be 100 times 2000, that will be about 200,000 ton, okay, and that 200,000 ton will be about 91,000 kilograms. So we are using the kilogram SI units, the calculations which I have highlighted over here. A wheel tractor weighs this much kilogram weight, is being operated on a haul road with a tire penetration of 2 inch, that is 5 centimeter. So remember that we have this formula here for the tire penetration. So if we have this these machines which have the tires over here, and we will be knowing that how much these tires are penetrating into the machine, how many centimeters, 6 centimeter or whatever. So 6 multiplied by the centimeter in the penetration. So therefore, let's go back to this example, which has about 5 centimeter penetration. What is the total resistance in kilogram and effective grade when the scraper is ascending a slope of 5%, or on the other hand, when the scraper is descending a slope of 5%? Okay, So first of all, we will determine the rolling resistance factor. So the rolling resistance factor will be equal to 20 plus 6 times 5. Okay, remember that we can use, okay, remember that we can use either this table or this equation, okay, in terms of the, for finding the rolling resistance. So the rolling resistance is equal to 20 times 20 plus 6 times the number of centimeters of the penetration. So depending on the data, the type of equation we will use. So the rolling resistance factor will be 20 times 20 plus 6 times the 5 centimeter was the penetration of the tire penetration. Okay, 5 centimeter tire penetration. So 6 times 5 is 30 plus 20, which is equal to 50 kilogram per ton. So 50 kilogram per ton of the weight, that will be the rolling resistance. So 50 kilogram per ton, and then total and the weight of the machine is 91 ton. So it is ton cancels with ton, so it will be 91 times 50. So the rolling resistance is 4,550 kilogram. Okay, so that will be the rolling resistance. So this rolling resistance here. Then what do we need to find? So what is the total resistance and effective grade when the scraper is? So if the rolling resistance is there, then what is the effective grade resistance? So the grade resistance is equal to 91 ton, which is the weight of the machine, multiplied by 1,000 kilogram per ton, because in 1 ton we have 1,000 kilogram. So we have multiplied it into the kilogram. So that is the total weight in kilogram, and multiplied by 0.05, which is the 5% slope. So more is the percentage of slope, more will be the grade resistance. So 5% slope. So in that situation, what we have over here is 91,000 multiplied by 0.05. So the grade resistance will be 4,550 kilogram. So now the grade resistance is 4,550 kilogram, and the rolling resistance is also 4,550 kilogram. So the total resistance will be 9,100 kilogram in this case. So this is the answer for part A. The effective grade in this case will be 10%, because both are equivalent. Effective grade will be 5% is the grade from the surface, plus 100 divided by 20. So where is this 100? So the formula is here. Rolling resistance factor divided by 10. Okay, so the rolling resistance factor was 50. Okay, and divided by 10. 50 divided by 10. Okay, so grade percentage and the rolling resistance factor. So here we have seen that the effective grade will be equal to 5 plus 50 divided by 10. So that will be 10%. In this case, it is only given in terms of the it is only given in terms of the US customary units, but in terms of the SI units, so you will use 5 plus 50 divided by 10, the other formula from equation 4.7. B. So these were the answers for part A. In part B, the grade resistance will be negative because we are moving downwards, descending. This is a descending slope. So since this is a descending slope, so the grade resistance will be down, negative. So it will be minus 4,550 kilograms. So the total resistance will be minus 4,550 plus 4,550, that will be 0. And the effective grade will be also become 0 because both are cancelling with each other. Okay, that is the rolling resistance and the grade resistance are cancelling with each other. So in this case, the effective grade will be 0%. So using these simple formulae, we can use we can calculate the rolling resistance and the grade resistance for the track. So remember that geometrically we can take this grade in terms of the percentage. So that means what is the percentage grade? So the percentage grade is like this. We draw this horizontal line. So if I draw this horizontal line and then this is the grade line. So the percentage grade is the vertical distance divided by the horizontal distance. It is y over x. So it is actually a tangent theta. It is actually a tangent theta. So basically y over x value, that is the grade percentage value represented in terms of the percentage. Grade represented in terms of the percentage is tangent theta value. But since these angles are normally smaller, so we are basically taking them as in terms of the percentage value instead of taking them in terms of the tangent theta value. So geometrically the formulas are based on this concept. Okay, so this was example 4-1. Example 4-2. Okay, a crawler truck, a crawler tractor weighing 36 ton is towing a rubber tired scraper weighing 45.5 ton up a grade of 4%. So what is the total resistance in kilogram of the combination if the rolling resistance factor is 50 kilogram per ton? So the rolling resistance in this case will be equal to 45.5 ton, which is the weight which is being towed. Okay, so 45.5 ton load will be towed. 45.5 ton load will be towed, and then this is 50 kilogram per ton. So the rolling resistance factor is given as 15 kilogram per ton. We don't have to calculate it in this term here, because in the previous example we calculated it. We used the penetration of the tire, that formula. But since it is given over here, so the rolling resistance will be 2,275 kilogram. The grade resistance will be equal to this 81.5 times 1,000 kilogram. Where is 81.5? 81.5, the grade resistance is In the grade resistance, yes, in the grade resistance, you will take the total weight of this roller tractor and the scraper. So that's why we have took the 81.5, because in the grade, both of those tractor and the scraper will have to move. So for example, there is this tractor, and then tractor is pulling a scraper. Tractor is pulling a scraper. So tractor weight is 36 ton. Scraper weight is 45.5 ton. So the total resistance will be total weight of this combination will be 36 plus 45.5, which is 81.5. So 81.5 ton multiplied by 1000 kilogram per ton multiplied by 4%, which is the upward grade. So it will be 3260 kilograms. So the total resistance will be equal to the rolling resistance plus the grade resistance. Okay, the total resistance will be 5535. So therefore, remember that in the rolling resistance, you will not consider the crawler mounted. So this is because this was the crawler tractor. Okay, here it said that we neglect the crawler because crawler is like a this type of machine. Okay, that means this is a crawler. So crawler are designed to overcome the rolling resistance. So therefore, we will not consider any rolling resistance for the crawler. So therefore, in this case, we have only taken care of the load of the weight of the scraper. So the scrapers are tire operated. Okay, scrapers are supported on the tires. Okay, so tires will have the rolling resistance, which is given as like 50 kilogram per ton. Okay, which is given as 50 kilogram per ton. So you have to be uh, careful that which factor we have to use where. Okay, so next we have to calculate the equipment travel time. Remember that at the very beginning we have talked about the cycle time. We have talked about the cycle time, fixed time, variable time, etc. So now let's talk about the equipment travel time. So earlier we just talked about the grading resistances. Okay, so yeah. So in the estimating equipment travel time, first of all, effect of altitude. So an internal combustion engines lose power as their elevation above sea level increases because of the decreased density of air at higher elevations. Yeah, so at higher elevation, so for example, on the uh, where we are at a very high above the sea level, the performance of the engines will be less compared with those areas where we are at the sea level. So in those situations, we will calculate the D rating factors. So D rating means a decrease in ratings. Okay, D rating means decrease in the rating of the engine in terms of the percentage. So that means how many percentage the capacity, the performance of the engine will decrease. So this will be given by the altitude in meters minus 915 divided by 100. So this is a more like an empirical formula. Okay, so whatever, for example, the altitude is here, then that D rating factor can be calculated by this formula. Then there is another factor which is called as the effect of traction. The power available to move a vehicle and its load is expressed as a rim pull for vehicles and drawbar pull for crawler tractors. So this is how these are some of the terminologies in which we represent the effect of traction. That is for pulling action on the wheel or for drawing action on the wheel. So in this case, the formula is the maximum usable pull is equal to the coefficient of traction multiplied by the weight on drivers. Okay, so this is the formula which is used. This formula will be more clear when we will be performing one example later on. Table 4-2. Typical values of the coefficient of fractions can be determined by this table. So if the type, depending on the type of surface, and if there are the rubber tires or if there are some tracks, then the coefficient of traction can be calculated from this table. So let's see this one example. Okay, then it says that a four-wheel drive tractor weighs 20,000 kilogram. 20,000 kilogram and produces a maximum rim pull of 18,160 kilogram at sea level. So the tractor is being operated at an altitude of 3,050 meter on wet earth. So on wet earth. So a pull of 10,000 kilogram is required to move the tractor and its load. Okay, 10,000 kilogram pull is required to move the tractor and its load. Can the tractor perform under these conditions? So we have to find it. So in this case, we will use those equation 4-8 to estimate the altitude deviation. So first calculate the deviation factor. So the deviation factor can be calculated by the equation, which is this. Okay. First calculate the deviation factor, which will give the effect of the decrease in power by the altitude. So the altitude was 3,050 meter and minus 915 from the formula divided by 102. That is also from the formula. So this will give us about 21%. 21%. So percentage rated power available will be then 79% because 21% power has been decreased. So the maximum available power is then 18,160 because 18,160 was the rim pull at the sea level. So if at the sea level is 18,160 meter, so at the 3,050 meter depth height, it will be 79% of that. So this will be 14,346 kilograms. So this four-wheel driver tractor can only pull up to 14,346 kilograms. Okay, 14,346 kilograms. So now on the other hand, let's find what is the coefficient of traction. So coefficient of traction we can find from table 4-2 because it was a wet earth. So we look at the wet earth. So where is the wet earth? Yeah, earth or clay which is wet. So it is for 0.45. Okay, and this is for the rubber tire. Okay, remember that this is for the rubber tire. So a four-wheel drive tractor weighs this and produces a maximum rim pull of 40,000 pounds at sea level. The tractor is being operated at an altitude of this on Earth. The pull is required to move the tractor and its load. Can the tractor perform under these conditions? So we suppose that this tractor is not on the track. Of course, if it was on the track, then it would be mentioned. So it will be on the rubber tire. So the coefficient of traction will be 0.45. So now we will use this coefficient of traction 0.45 and then multiply it with the 20,000 pound. That means about its weight. That means, so then it is 20,000 pound. Okay, 20,000 multiplied by 0.45. So it is 9,000 kilograms. So the maximum usable pull in this case is 9,000 kilograms. So the maximum usable, because the maximum pull as limited by traction is less than the required pull. So the tractor cannot perform under these conditions. So for the tractor to operate, it would be necessary to reduce the required pull, that is the total resistance, increase the coefficient of traction, or increase the tractor's weight on the drivers. So in this case, since this value 9,000 maximum usable pull, maximum usable pull is less than the maximum available power. So this cannot be, the tractor cannot perform under these conditions. So because the maximum pull as limited by traction is less than the required pull, that means the required pull is 14,346 kilograms. Okay, and therefore this tractor cannot perform under these conditions. So some of the steps which can be taken to improve this situation has been given, like tractor's weight on the driver, increase the coefficient of traction, like that. It should be improved. Okay, so this was the four-wheel drive tractor. So again, we need to estimate the equipment travel time. So for this, we can use the performance and retarder curves over here. Yeah, so this type of curve is can be used for some machinery. It's a typical crawler tractor performance curves. So if for a crawler tractor, then usually the speed is much less. Okay, here you can see that this chart for the speed only shows a speed from about 0 to 12 kilometers per hour, and under different drawbar pull conditions and for different types of gears. So we can use this to calculate the speed of the crawler trucks. And then there will be a use of this chart in the examples. So example 4-4. So use the performance curve of figure 4-1, that is this one, to determine the maximum speed of the tractor when the required pull is 27,240 kilograms. Okay, so if the required pull is 27, that means if this crawler truck pulls 27,240. So what is the required speed in this case? So 27,000 will be somewhere here. So maybe it will touch somewhere here, and then on the horizontal axis, it will touch like this. So it will show that the speed will be this much, okay, which will be given over here. So from figure 4-1, at a drawbar pull of 27,240 kilograms, and move horizontally until you intersect the curves for the first and second gear. So read the corresponding speeds of 1 miles per hour, about 1.6 kilometer per hour, and for second gear, and 1.5 miles per hour for the first gear, okay, or 2.4 kilometer hour for the first gear. So the maximum possible speed is therefore 2.4 kilometer per hour in the first gear. So in this case, the maximum possible speed is 2.4 kilometer per hour. So in those situations, then when this much pull is required, so according to this chart, so the tractor can be performed at a maximum speed of about 2.4 kilometer per hour, as given by this chart over here. So we can read this speed value over here, like 2.4 kilometer per hour. So this chart can be used to calculate the speed of the machine or the tractor or the truck, but of course not for the truck. This chart can be used for the typical crawler mounted machines, which move relatively slowly. There are some other curves as well. So for wheeled tractors, okay. So the previous chart was for the crawler tractors, but this chart is for the wheeled tractors. So this chart can be also used. So the wheeled tractors, we have several gears, not just the first, second, and the third gear. It may have like fourth, fifth, sixth, seventh, eighth gears as well. And there will be some rim pull over here. There on the top, the gross weight has been given, and then there are some certain rating curves, okay, for the grades, okay, 8%, 2%, 5%, 8%, 6%, etc. So this is a very comprehensive type of chart for the calculation of the wheel scraper performance curve. So this chart is called as the wheel scraper performance curve. Another chart over here is for the wheel scraper retarder curve as well. So let's see example 4-5. Okay, using the performance curves of figure 4-2, figure 4-2, where is this figure? This one, okay, this figure. Determine the maximum speed of the vehicle if its gross weight is 68,000 kilograms. The total resistance is 10%, and the altitude derating factor is 25%. Okay, so start on the top scale with a weight of 68,000 kilogram. Drop vertically to intersect the 10% grade line. Okay, 10% grade line, and move horizontally to find and move. Start on the top scale with a weight of 15,000 kilograms, 68,000 kilograms. So 68,000 kilograms is where. So the weights are given as over here, gross weight. Yeah, in the weights are given in kilograms. So 68,000 will be here. And then we have to move vertically downward to hit the line for 10%. Right. So this is the 10% time is here. Yeah, to hit the line for 10% over here. So we can use it more better with the help of some scale or ruler scale. Here it is very difficult for me to draw this vertical line from here. But anyway, so I have hit the line for 10% over here, and then what we have to do is to intersect to the line and then move horizontally to find a required pull of 6,800 kilograms. Okay, so we have to move horizontally from here. So from here, move horizontally, and then we can get a pull of about 6,800. Okay, with somewhere between 5 and 10. So we can estimate that it is about 6,800 kilograms. And then on the left scale, so divide 66,800 kilogram by 0.75. Yeah, so we have to divide it by 0.75 because the derating factor is 25%. So that means 1 minus the derating factor to obtain an adjusted required pull of 9,080 kilograms. So that means we need 9,080 kilogram over here. So from here, we can move to 9,080. So over here. So here we can intersect these first gear, second gear, and the third gear lines. So these will, and then from the downwards, then we can see their speeds. So at this weight level, then we can read the speeds over here. So, and move horizontally to intersect the first, second, and the third gear curves. So drop vertically from the point of intersection with the third gear curve to find a maximum speed of about 10 kilometers per hour. So the maximum speed will come at about third gear. That means over here for the third gear, about 10 kilometers per hour. Okay, 10 kilometers per hour. So in this way, we can find the speed, maximum speed for this weight level in the equipment which are used on the wheels. Okay. So this was example 4-5. So again, this topic will continue in the next week. So that is what we will do today. So do you have any question about this?